Dat Seaboy said. At Saf. Dat Seaboy said. Hop in when you're ready.
Rare.
Ha, ha, ha. ha, ha, ha.
Saf said, ready now, P.
Here, wait, give me 1 second. Because I didn't expect that. I was gonna say I forgot, about what we're doing. So, let me, let me set a timer for an hour and 20 minutes because the next stock auction is at that time. And then, yeah.
Tell me when to start.
Well, I mean, you can, if you have, like, if you're gonna be screen sharing,
I am screen sharing.
okay, shoot, ba, 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 doop, ba, doop, beep, ba, doop. Typing guest. I invited Avi as well because we were talking about something else that may or may not interest you. It might actually. I don't know. Well, we'll see if he makes it. Doink. Let's see. Okay, so we'll just do that. Actually, we'll just do this. I am in. So.
Let's say that this is you. You're enjoying a nice sunny day, and you decide to take a nice long.
Saf
yeah.
Do you hear audio?
Yeah. Sorry, yeah. I can hear. I just knew that you started, and it's like I'll just if we're lungs.
Long, deep breath of air. And of course, when I say air, the part that you probably care the most about is just the oxygen part of that air, right? That's the part that we as humans need to survive. So you take a deep breath, and let's say that you take it through your mouth. You take a deep breath through your mouth. And then let's say you take one more deep breath, a second deep breath, and you take that one through your nose. Now you might think, well, these are two totally different ways of getting in air, right? That's certainly how it looks when you look at a mouth and a nose. It doesn't look like they have much in common. But the truth is that actually, if you follow the air, it almost follows an identical path, right? So the air is going to go into the back of the throat, really regardless of how you took it in. So here we have air coming in from the nose, and here you have air coming in from the mouth. And they meet up in the back of the throat. And then they go down, down, down. They go towards this thing that we call the Adam's apple. I'm going to bring up a little bit of the canvas so you can see it more easily. But basically, you bring up this, or you see this Adam's apple right here. And actually, you can go ahead and take a feel of your own Adam's apple. It's a pretty cool structure in the middle of your throat, and everybody has it. That's the first thing I want to tell you, is that everybody has it, not just men.
Yeah, I was gonna
say women have it too. And the reason it's called an Adam's apple, it's called an Adam's apple because Adam is a generally a boy's name.
Yeah.
And so it's to remind us that usually
men
or boys have larger Adam's apples than girls. And if you're trying to find it, I just also want to point out there's this notch here. And if you can feel the notch with your fingers, that gives you a nice clue as to where it's located. But this is this is it. This is the Adam's apple. And what it does is it helps you control your voice. And actually, another name for the Adam's apple, another name for it, is sometimes people call it the voice box. The voice box. And of course, air is passing through the voice box, and it's kind of the entryway into the trachea. And so it actually allows me to make my voice really high or make my voice very low, depending on how you change the muscles around in that Adam's apple. So that's actually the kind of first cool thing I want to point out to you, is that you can actually control your voice. I'm sure you knew this already, but what you're using is your Adam's apple or your voice box. Now, air keeps going, right? Air is just going to keep making its journey down, and specifically, of course, the part of air I said, we care about is the oxygen. It's going to keep making its journey down into the lung area. So this is now the lung area. It's gone down the trachea, and it goes into the two lungs, the right and left lung. This is the left lung. I'm going to put L for left, and this is the right lung. I'll put R for right. And immediately you're thinking, well, wait a second, aren't they switched? Now I want you to remember that this is from the perspective of the person who owns the lungs. So that's why I'm putting left where I put it and right where I put it. Now, we should probably go ahead and start labeling some of this. You can see that the lungs actually don't look identical, right? They look slightly different. For example, this one has 3 lobes. The right side has 3 lobes. We call it the upper lobe, middle lobe, and lower lobe. And the left one only has 2 lobes. So that's the first kind of big difference. And the other difference is that you actually have this thing in the middle that we call a cardiac notch. This thing right here. This is called the cardiac notch. And the reason we call it that is that it's a little spot that gets formed because the heart is literally kind of peeking out here. And as a result, it kind of makes a notch in the lungs when it develops. So the heart takes up a little bit of space here. This is our heart. And as a result, it takes or makes that notch. So this is our heart space here. So on the other side, you've got, of course, your 2 lobes, your upper and lower lobe. And these are 2 clues. So if you ever see a lung just kind of sitting by itself and you want to figure out whether it's the left lung or the right lung, you can look for the lobes, the number of lobes, or you can look for that cardiac notch. Now, around here, around these lungs, you've got ribs, right? So you've got ribs here, and between the ribs, you've got rib muscles, and they're, of course, on both sides. And below the lungs and below the heart, you've got a muscle, a big muscle. Actually, it's going to come through here. I'm going to just kind of go through the word heart, and it basically becomes the floor. So the heart and the 2 lungs, they sit on this floor made up of this muscle, and this muscle is the diaphragm muscle. So this diaphragm muscle makes up the floor. The ribs make up the walls. So what do we have? We have basically a room. We have a giant room with walls and a floor, and this entire room we actually call the thorax. So within this room, then you have your 2 lungs and your heart. So far so good, but I haven't done a very nice job of actually showing you where the air goes. I've just kind of pointed that it goes to the 2 lungs, but you don't actually get to see where it goes after that. So I'm going to erase a lot of this. I'm going to reveal to you what it would look like if you could slip on some X-ray glasses and look at your 2 lungs. This is kind of what it would look like, right? You've got all of this interesting architecture. And the easiest way to kind of think about this, probably the simplest way to think about this, is to imagine a tree. So imagine a tree, and that tree has been flipped upside down. So you've got all these branches off that tree, and they're branching and branching. And if you flip this tree upside down, you start seeing that it looks a lot like what we have in our lungs. Our lungs basically look like a flipped upside down tree. And we even call it that. We even call this entire structure, we call it a bronchial tree. So when you look at the lungs and they look kind of messy or complicated, just think of them as an upside down bronchial tree, and all of a sudden it'll look much simpler. With basically in the middle, you've got this nice trunk, right? This is our trunk, and then it starts kind of branching from there. So air goes down this main trunk, this trachea, and then it kind of starts splitting up. And each of these kind of colored regions, the green region or the purple region, serves a different lobe. So this green region serves the lower lobe down here. The purple serves the upper lobe. And on this side, you've got an upper, a middle, and a lower lobe. Now, I know it looks a little bit strange because you've got some green branches in what should be the middle lobe, like right here. You've got some orange branches in what looks like the upper lobe, like right there. But what you have to remember, and this is kind of tricky to do, and just try to play with it in your head, what you have to remember is that what you have is basically a three-dimensional lung. So you have to imagine that we're only looking at it from the front side, but of course that middle lobe does go back. And if it went back, then you'd make perfect sense why the orange branches are where they're at. Now let me continue the air journey because I want to make sure we finish it off. So let's say we take a little branch like this, right? We expand it, we keep, going, zooming into it, zooming into it, zooming into it until it's microscopic. You can't see with your eyes anymore, but you could see it under a microscope. It would look like this. It would basically, under a microscope, it would look like a bunch of little sacs, like this. And these sacs, we call these alveoli. Alveoli. And the air actually kind of runs into the alveoli. It has a dead end, and then it comes back around. And then you breathe it out. So that's how breathing works. The air goes all the way in from your mouth down to the alveoli, takes a U-turn, and then goes back out. But before it does that, before it leaves, very close to the alveoli is blood. And let's say blood is coming this way and going that way. And what will happen is that actually out of the, or into the blood, let's do that first, will go oxygen. Oxygen will actually go into the blood.
What?
And out of the blood will be waste. So you'll have some carbon dioxide waste that your cells have been making. And that waste actually then gets thrown back into the alveoli.
That makes sense.
So now you can see how oxygen gets from the outside world, gets breathed in through the lungs when you inhale, gets down into the alveoli, exchanges with the blood, and then you exhale and let all that carbon dioxide out.
Well, there you go. Is that it? Is that... Oh, there we go. That's it. Okay. And we're just gonna keep
a
going.
classic
Okay.
story out there, and it has to do with a character named Jack. And you may have heard this story, but I'm sure that there's parts of that story that you have not heard. And so I'm actually going to just try to fill in those parts so that you get a complete idea of what happened. Now, Jack came across, a long time ago, a famous, now famous beanstalk, right? So this beanstalk was growing and growing and had these huge leaves. And actually, Jack used these leaves to make his way up this beanstalk. And so this is how this beanstalk became very famous, because it basically allowed Jack to use it like a ladder. Now, the part that we don't hear about is what was going on between Jack and the beanstalk. He was exercising, right? So he was actually making a lot of carbon dioxide, right? He was making a lot of this gas, this carbon dioxide gas, as kind of a waste product as he was running, scampering up the beanstalk. And the beanstalk was helping him physically, but also was actually providing him with very precious oxygen. In fact, if the beanstalk didn't do that, he may not have even made it. And we don't know for sure, but we think that perhaps some of the story may have taken place during the day. And in fact, we know that sunlight is quite important for this process, and we think that this process, the name that we give it, for the beanstalk anyway, is photosynthesis. Photosynthesis. And so what is really happening, we're actually going to kind of write it out here, between Jack and the beanstalk, and really between all plants and animals. What is this process between them? We know that on the one hand you have beanstalks doing photosynthesis, and on the other hand you have folks like Jack doing cellular respiration, right? And there's this really kind of interesting symbiosis, and by that I just mean that the two are kind of relying on each other to really work, right? So you kind of need both of them to work well. And so let's actually take a moment to write out these processes that are happening between Jack and the beanstalk. So let's start with the process of photosynthesis, the beanstalk. So
Should get back
on
in
the
my
one
room.
hand, you've got what? You've got water, because of course the beanstalk needs water, and you've got
Yeah,
carbon
okay,
dioxide. And I'm going to do carbon dioxide in orange. So it's taking in water and carbon dioxide, and it's going to put out, it's going to actually take these ingredients, if you want to think of it as kind of cooking, it's going to take these ingredients and it's going to put out what? Oxygen and glucose. So I'll put glucose up top and oxygen down below. So these are the inputs and outputs of photosynthesis, right? And on the other side, you've got something very similar. You've got inputs, you've got glucose and oxygen going in. You're going to start seeing some serious similarities here. You've got glucose and oxygen going in, so Jack is taking in those two things. And he's, again, of course, processing them. And he's putting out water and carbon dioxide. So this looks really, really nice, right? It looks perfect, actually, because everything is nice and balanced, and you can see how it makes perfect sense that not only did Jack need the beanstalk, but actually it sounds like the beanstalk needed Jack, based on how I've drawn it. Now remember, none of this would even happen if there was no sunlight, so we actually need light energy. In fact, that's the whole purpose of this, right? Getting energy. So you have to have some light energy. I'm going to put a big plus sign, and I might even circle it because it's so important. I don't want you to lose track of it. And on the other side, of course, Jack is getting something as well. He's getting chemical energy. Chemical energy. In fact, he's using the chemical energy to help him climb the beanstalk. And so the chemical energy comes in the form of what we call ATP, which is just a molecule of high energy. And so Jack is basically, or Jack and the beanstalk are basically going from light energy to chemical energy using these two equations. Now here's the part that people don't always appreciate, and I'm actually going to take just a moment to show you that this isn't the full story. There's actually something else going on as well, and that is that there's actually some cellular respiration happening on the plant side. So remember, not only does the human or the Jack need energy, but so does the plant, right? The plant needs energy as well. And in fact, if it takes in light energy right here, it needs to find a way to actually eventually get some chemical energy itself so that it can do all the things it needs to do. Like, it doesn't need to run because plants don't move in that sense, but it might need to make new roots and it may need to make a flower, and all these things take energy. So actually, photosynthesis is happening during the day, right? This is happening during the day. But at all times, plants are also capable of doing cellular respiration, just like humans are. So humans and plants have actually more in common than you might think. So this brings up an obvious question. Why in the world would a plant send its glucose and oxygen this way when it needs it itself? Why would it actually get rid of it? Well, the truth is that the glucose ends up oftentimes in fruits and vegetables that we cannot eat. But as far as the oxygen goes, it makes an excess of oxygen. So there is actually enough oxygen to go both to us or to Jack and to be used by itself. So it actually has an excess of oxygen that it's making. So that's actually kind of interesting and good to know. Now, if you think about it, if I was to, let's say, sketch out a planet, let's draw out a little planet over here, and ask you the question, if this was your planet Earth, and you've got thousands instead of just one Jack, let's say now you have thousands of Jacks and thousands of beanstalks, in fact, not even thousands, let's say billions, because really that's what we have, right? We have a planet full of humans and full of other animals and full of plants. What would the atmosphere look like? This is the atmosphere. What would the atmosphere look like? Well, you'd guess that the atmosphere is gas, and so what would those gases be? Well, the way I've kind of drawn things again, it looks like I've got lots of oxygen and lots of carbon dioxide. So I would say, well, I guess there must be, I don't know, maybe 50-50 carbon dioxide and oxygen based on what we know so far.
Maybe more
And the truth is that
points.
that's actually not true. That if you actually look at air, if you actually kind of break down the
Oh,
atmosphere or air, I'm just going to write air here. If you actually break it down, it turns out that the ratios are actually a little different. So, for example, oxygen makes up about 21% of our air. This is
yeah,
our
there's more carbon
air
dioxide.
breakdown, air. And carbon dioxide makes up about less than 1%. So that leaves you
What?
wondering what the heck is making up all that other uh, parts of air? What is it made of? And it turns out it's about 78% nitrogen.
Oh,
Nitrogen. Now you know you've got nitrogen in your proteins. We've got nitrogen in
wait.
our DNA. So nitrogen is part of us, and it's part of
Hmm.
many living things. But nitrogen gas specifically is actually N2. And N2, this nitrogen gas, really is not too reactive. It kind of just hangs out by itself, does not like to react with things. So, looking at our little atmosphere graph, if you want to now think about it, knowing that we've got very little carbon dioxide and about 21% oxygen, you could think of oxygen kind of being, let's say, something like that. Well, then
Hmm.
relative to that, nitrogen would be,
Well,
much more, right? You have much more
it's-
nitrogen hanging
yeah.
out.
I mean, it's
And
just
so
simple
this is really
pie
what our
graph or
atmosphere
something.
looks like. It looks more filled with nitrogen than anything
Hmm.
else. And in terms
And
of carbon
then
dioxide, it's just
carbon
got a little smidge of
dioxide,
carbon dioxide, maybe right there. That
or
could be
just
carbon
little
dioxide, maybe
dots.
even less than that. So this is really what our atmosphere looks like visually. And the nitrogen, again, it's making up the majority. And if you actually kind of wonder where all that nitrogen is coming from, because I didn't mention it in any of the equations,
Yeah.
right? Most of that
Space.
nitrogen has been around, scientists think, since the beginning of when Earth even had an atmosphere. And
Yeah.
that nitrogen we're just kind of carrying with us at all times. And that's why it just kind of remains around 78%
Mm.
and will probably remain there for many, many years to come.
So wait, is that are we just gonna what I was gonna say? How much what staff? Staff, are you cheeky? Crap. So, how many more you need to do?
Dat Boy said. At Saf, how many more you need to do?
Gosh.
Saf said. 5. Dat Boy said. All of them? RALR. Saf said. I'm just completing an assignment RQ. Dat Boy said. Is there more to it or just the videos?
Oh, crap.
Dat Boy said. I assume this is IRL, paper-based.
Crap.
Saf said, different tab.
Oh.
Just the video's ATM. Ready to start again? Dat Seaboy said, sure.
So here's a little person, and I've drawn their face, and you can see in blue at the bottom I've drawn their voice box. And I'm going to show you exactly what happens when you draw a little molecule like this of oxygen and follow it along its journey. So it's going to be breathed in either through the nose or through the mouth. And you know it's going to kind of end up in the same place, or so we think, right? We said that basically kind of the back of the throat is where it's going to end up. And this is my nose kind of going to the back of the throat, and the mouth kind of empties into the same spot. But already there are going to be some differences. So for example, you have in your nose these little yellow nose hairs. And the first question, of course, people think of with nose hairs is, what the heck is their purpose? What do they do? And nose hairs are part of our filter system. So we have this great filter system, and there's nose hair, and their job is to make sure that all of the kind of large particles of dirt and dust are kind of picked up. So they're good for getting all the large particles out of the air, so it's cleaned up. And then you also have this kind of green slime, right? This kind of green mucus that we all kind of make. And this mucus, sometimes you think of it as snot. This snot or mucus is good for small particles because it's really sticky. And the small particles of dust and dirt are going to glom onto it. And so that is our way of kind of cleaning up the air so that when we breathe in through our nose, the air is basically clean, or at least cleaner than it would be otherwise. And so, of course, if you compared nose air, or the air that you breathe in through your nose, to air that you breathe in through your mouth, the mouth air will be, of course, a little dirtier because they didn't have that nice filter system. And kind of thinking along the same route, if you think about picking your nose, that would be basically kind of cleaning the filter, right? So that's kind of a new way maybe of thinking about that habit. So air is going to end up going to the back of the throat. So air is going to kind of go in this way, and our little molecule of oxygen is going to kind of end up at the back of the throat. And another kind of interesting difference is that already that oxygen molecule and the air around it is going to be slightly different in other ways. It's going to be cleaner if it went through the nose, but either way, nose or mouth, it's going to be warmer and also more moist. So that's another change. In comparison, on the outside, the air is a little colder, and drier. So these are some key differences in terms of what's happening to the air. These are two major differences, right? So now the air, or our little molecule of oxygen, has got a choice. It can either go kind of down one of two paths. One I'm going to draw is going to be into the larynx. This is our larynx right here. And we also call our larynx our voice box. So you might remember that was the name I had mentioned previously. Voice box, or larynx is kind of the more medical word, I guess. And sitting over the larynx is the epiglottis. The epiglottis. And the epiglottis is basically like a lid, kind of protecting the larynx from making sure that food and water don't go into it. Now there's another tube I just alluded to, and it's sitting right here. And this purple tube is our esophagus. So the esophagus is basically, it's fantastic for things like food and water. You want food and water to go down the esophagus because it's going to lead to the stomach. So you want food and water to go that way, but you don't want food and water to go into the larynx. And so you want to make sure that the epiglottis, that lid, is working really well. And if food and water, if you're swallowing food and water, this epiglottis will literally just kind of close up and protect your larynx. But in this case, that's not happening, right? We're not actually food and water. We're a little molecule of oxygen. So let's follow that molecule a little bit further down. Let's see what happens to it. I'm going to drag up the canvas a little bit, just make a little bit of space. And I want to just stop it right there because I want to show you that the air molecule, or the oxygen molecule, has already kind of made an interesting crossroads. It's actually kind of broken an important boundary. And that's this boundary right here. And on the top of this boundary, I've included the larynx, and of course all the other stuff we just talked about, the mouth and the nose. And this is considered our upper respiratory tract. So anything above this dashed line is our upper respiratory tract. And then of course you can then guess that anything below the line must then be our lower respiratory tract. So this is an important boundary because people will talk about the upper and lower tract, and I want to make sure you know what is on which side. So on the top of it is the larynx and everything above that, and below it is the trachea. Let me label that here. The trachea is right here, the windpipe, or the trachea, and everything below that, which of course mainly includes things like the lungs, but as we'll see, a few other structures that we're going to name. So I'm going to keep moving down, but now you know that important boundary exists. So now let me just make a little bit more space so you can see the entire lungs. You can see the molecule is going to go through the trachea, and actually I have my left lung incompletely drawn. Let me just finish it off right there. So we have our right and left lung, right? These are the two lungs, and our air is going to just kind of slowly pass down. Our molecule of oxygen is going to pass down, and it's going to go either into the right lung or the left lung. Now here I want to make sure I just take a quick pause and show you the naming structure. And the important word of the day is the bronchi, which alludes to one, or sorry, I screwed it up already. The bronchi, which alludes to more than one, sorry about that, and bronchus, which alludes to one. So bronchi means more than one, and bronchus means one. So just keep track of these letters, I and US, okay? So if we say that, for example, we are going into this area right here. Let me just choose a new color so it's really clear. This will be our main. If we go into this spot, let's say our air molecule or our oxygen molecule goes this way, then we would say it's in our left main. I'm just going to underline it as I go, left main bronchus. That's what we would call that. And then if it went further, let's say it went down here, then instead of calling it main, I would call it the lobar. That's the word here. So I'd say it's my left lobar bronchus. And then if I wanted to go a little bit further, I could say, well, now this is my segmental. So these are the words that we use. And this final one would be then my left segmental bronchus. And of course, if you want to talk about two of them, let's say I want to talk about, both this guy and this guy, then I would say those are my right segmental bronchi, because now I have to use the top word because it's plural. So that's the naming structure. And another kind of important naming structure you'll sometimes see is primary bronchus, secondary bronchus, and segmental they call tertiary bronchus. So you'll see either one of those, but I'm going to stick to main, lobar, and segmental because I think it's a little bit easier and more intuitive to remember it that way. Now, there are a couple important, interesting things happening already. So right here, this notch, or this point right here, this is our carina. This is our carina. So at the carina, you have your break between the right and left main bronchus. And what I want to point out to you is that this is a little bit more vertical. This right-sided one is a little bit more vertical, and the left-sided one is a little bit more lateral. This is a little bit more flat or lateral. So it's kind of a cool thing to know, which is that if something was to slide down the throat, let's say a penny or a peanut or something was to slide down here, it's more likely to go down this way simply because of gravity. So gravity is going to push things towards the right main bronchus more than the left main bronchus because the right main bronchus is a little bit more vertical. That's kind of a fun fact that you now know. And we should actually, I guess I didn't do this already, but we should actually take a break and make sure we name some of these things. Remember, this is called our cardiac notch. Cardiac notch. And remember that that's one clue to kind of telling apart the left and right lung. And the other clue we said was the lobe. So of course the right one has the upper lobe, the middle lobe, and the lower lobe. And the left lung only has the upper and lower. So that's an important clue. I just want to make sure we don't forget our little tricks that we've learned for telling apart the lungs. So I'm going to take a little pause there, and now I'm going to show you in a sped up version all of the different branch points. So for example, here we have just a couple branch points, right? 1, 2, and getting into the segmental bronchi would be the third branch point. But I'm going to speed things along and show you how many more branch points there actually are before we get to the final part of our lung where the gas actually happens. So enjoy.
Oh, alright. Oh crap. Oh crap.
Going back to
Alright.
the very
Crap.
point where we left off, we start with kind of a bronchi, right? And we said that there is a naming structure for how to name the bronchi, but that's really just the first 3 branches. And then after the first 3 branches, all of the orange stuff, all of those branches going from branch point 4 all the way down to about branch point 20, those are the conducting bronchioles. So that's the name we give them. They're no longer bronchioles. And so if you see that word, just keep that in mind, that we're a little bit further along in the lungs. And then after the conducting bronchioles, you get into a few more branch points, and we call them the respiratory bronchioles. And actually the final, I should mention this, the final conducting bronchiole, sometimes you'll see this called the terminal bronchiole. It's a bad name because terminal sounds like we're done, but actually we're just done with the conducting bronchioles, and we're still kind of going into the bronchioles. I guess if I'm only into one, I should just probably make it singular. And then finally you get into the alveolar ducts and the alveolar, which is kind of a few alveoli put together. And if it's plural is alveoli, then singular, just talking about one little part of that sac, would be alveolus. So that's where our little molecule of oxygen ends up. And this is kind of where it ends up before it's going to participate in gas exchange. Now, this entire area going from respiratory bronchioles on downwards, this is all called the respiratory zone, and anything above that is considered the conducting zone. So anything above that, and that not just the conducting bronchioles, but conducting bronchiole, and then all the stuff of it, bronchi, and even the larynx, and the mouth, and the throat. That's all considered part of the conducting zone. So basically, Oxygen is going to come through the entire conducting zone, everything we just talked about, and is going to go down into the respiratory zone. And finally, a molecule of oxygen is going to be very happy to have finally made it to the very end of the bronchial tree and is ready for gas exchange now.
Dat Boy said. At Saf, why are you deft again, by the way? Saf said. Oh yeah, guess I can undeafen now I've done my assignment.
Oh, really? Wait, is that what? Oh, because for a second I was like, what assignment? What is that? So I was like, oh, I wish we could actually, talk and stuff. So,
Was just a writing assignment.
okay. Well, and then I was like, oh, I didn't know if I thought it was like for the videos or thing, because I've been talking during the videos. I was like, wait a minute. So I'm not like hearing. I'm like talking during. I'm actually just like kind of listening, and at least the first one was kind of interesting because I was like, oh, yeah, breathing through the mouth and stuff.
MHM lol.
I forgot exactly what I was saying because it was, yeah. All right, let me.
If you could have a magical ability to actually see all of the air molecules in the air, you might see something like this. It would be a lot more crowded, but you could imagine it might look like this. And let's say that you actually decide to do something a little interesting, and that is to take a jar and simply capture some of the air molecules in your jar. So I've got my jar here, and I'm actually going to put a little opening on my jar. So let's say there's a little opening there, and I take that opening and I'm going to just make it kind of a stretched out neck. So this is my stretched out neck on my jar, and there's the opening to my jar. And on the other side, what I want to do is actually kind of compare what's going on inside of my jar to what's going on outside of the jar. So to make it fair, let me actually try to create a purple box, kind of a dashed line around an equivalent volume. So this is going to be basically a similarly sized part of the air. And of course, this dashed line is just to show you which part I'm talking about because, of course, this is an imaginary line. But let's say we're comparing what's going on inside of my blue jar with what's going on inside of this purple dashed line. Now, we know that that purple dashed line is kind of capturing a certain amount of the air in the atmosphere. And that air is going to have molecules that are bouncing off of each other. Let's say something like this. And you've got a bunch of kind of random collisions happening. And these collisions, the more frequently the collisions are happening, the higher the pressure in the air. And in fact, measured pressure in the air is around 760 millimeters of mercury. So that's how we think about air pressure. So that's the pressure in the atmosphere. And if I was to measure my jar pressure, it would be, of course, the same thing. It would be 760 millimeters of mercury. And as a quick aside, just thinking about what these molecules are, if there are 5 of them, then you might say that this is nitrogen, this one is nitrogen, this one is nitrogen, this could be nitrogen, and this one might be oxygen. Because remember, oxygen is about 21% of air, and so that might be a fair estimation of what these 5 molecules could be. Mostly nitrogen. So in the air, we've got nitrogen and oxygen. It's bouncing around in my jar just as it is in the atmosphere itself. And now let's say I decide to do kind of an interesting experiment. I decide to drop the floor. Just stay with me here. I drop the floor of my jar. So I actually expand the bottom of my jar. And for the moment, don't worry so much about how that could possibly happen. Let's just assume that I do creatively somehow kind of drop the floor. And now it looks a little bit lower. So the volume has gone up in my jar. And actually simultaneously, I should mention, just want to mention here, that this door or opening of my jar is closed at the moment. So my opening, I've put a lid on it. So that's closed and my floor just got a little bit lower. So the volume has gone up. That's the big change, right? Actually, let me write that up here in the corner. I'm just going to erase some of these molecules to create some space. And the first thing I want to mention is that the volume has gone up in my jar. So all of the green stuff I write in the corner is going to be from the jar's perspective. If the volume goes up now, if that's the case, then these molecules inside the jar, they're excited. They've got more room to kind of run around and play and not bump into each other. So if they're not bumping into each other as much, because of course they've got all this extra space down here, then the pressure on the inside of the jar is going to go down, right? Because there are less collisions happening. So now we've got, let's say, a slight decrease. It went to 757, so a little bit less than what's on the outside. So because the volume went up, the pressure went down. And again, that's because you have fewer collisions. And the new pressure is 757, which is a positive number. But sometimes people refer to this as negative pressure or a vacuum. And the reason they're saying that is because they're saying, well, relative to 760, relative to this number, 757 is 3 points lower. And so in that sense, it's negative. So if you actually want to look at them, compare them to each other, you'd say, well, 757 minus 760 is negative 3, and that would be a negative number. But for the time being, I'm just going to leave it in the numbers we have, which is 757. Now, let's say that I open this door. This opening is now open. If I open up this opening, what will happen? Well, we have all this extra space down here I circled, but I'm just going to kind of remove this for the time being. All this extra space. And molecules, of course, are being knocked around all the time. So these collisions are happening always. And some molecules are going to get knocked perfectly so that they actually kind of move into the jar. Let's say it goes in like this. So you're going to get some molecules that go in. And in fact, you might have some molecules that kind of get knocked right out. So it's going to happen constantly. But overall, what's going to be the net difference? Well, let's say I leave this and I kind of walk away and do my own thing for a minute and come back. I'm going to notice that there are actually extra molecules on the inside of my jar because there's more space, less crowding in my jar because of all that extra volume I created. So over time, there's going to be a few extra molecules in my jar. And maybe I got lucky and this one's an oxygen molecule. So I've got extra molecules on the inside. And these molecules, so actually that would be, I guess, the next step is that air molecules move in. Air molecules move in. And these molecules are now going to do what molecules do, which is kind of bounce off of each other. So they start bouncing off of each other. And all of a sudden, now you've got, let's say this guy collides over here as well. And maybe there's some bouncing and this collides over here. So now you've got, because you've got 6 molecules on the inside and, kind of the same volume, the pressure on the inside has gone up. So pressure has gone up on the inside of the jar simply because there are more molecules in there now. So even though you had more volume initially, you've kind of filled it up with more molecules. So the pressure goes up, let's say, to 760 millimeters of mercury. So now it's gone back up. So this is my new pressure. And this all happened, this whole kind of series of events happened because I decided to move the floor. Now, what would happen if I decide to move it back? Let's say I decide to kind of go back to the original floor size, and I kind of get rid of this lower line, and I raise the floor back up. And so now it looks something like this. Well, now the volume, this is kind of the new first step. What's going to happen? the volume has gone down. That's obvious because I just moved the floor purposefully. And I've got 6 molecules in my jar, and they're thrashing around, bumping into each other, but they've got less space to do it in. So the pressure is going to go up because there are more collisions. They're bumping into each other more. So the pressure is going to go up. Pressure is going to go up now to, let's say, 763 millimeters of mercury, because it was 760. And at this point, let's say this is closed up. And so the pressure on the inside is 763 millimeters of mercury. Let me erase this. And that's because, again, you have more molecules, but you reduce the volume. So then the pressure on the inside is actually now higher than the outside pressure. Remember, the outside pressure is always going to be around 760, and that's because the atmosphere is just enormous, right? So the movement of a few molecules this way or that way is really not going to change the amount of collisions that are happening in the atmosphere. That's always going to stay the same. And so if I was to open this door up, then some molecules, of course, are going to be bouncing around, and some of these things might kind of bounce out. So some molecules might kind of bounce out. And overall, again, on the whole, you're going to have more molecules bouncing out than bouncing in because you have more collisions happening on the inside. And again, when I say more collisions in your mind, I want you to think of higher pressure. So if there's higher pressure on the inside and more collisions happening on the inside, you're going to have more things bouncing off each other, and molecules are going to be sent outside. So the next step I could write in would be air molecules move out. Air molecules move out. So the final point is that if air molecules are moving out, let's say just by random chance this oxygen molecule happened to be the one that got sent away, so this one kind of got knocked out, then you have, I'm trying to erase all this to clear it up, then you have 5 molecules again on the inside, and you have the same kind of volume that we initially started out with. So the pressure on the inside goes back to what it was in the first place. The pressure falls to 760. And the reason that I say exactly 760 is because this process in step 3, this step will continue until the number of collisions on the inside and outside of the jar are equal. So this is kind of the process. And actually, I forgot to mention, when we were back at 763, sometimes people call this positive pressure. Positive pressure. For the same reason they called it negative before, because all they're doing is they're comparing 763 to atmospheric pressure, which is 760, and saying, wow, that's a +3. That's a little bit positive. And so when you compare things relatively, you use words like positive and negative. But if you're using just the total number in kind of absolute terms, then you would stick to 757 or 763. Now, what does all of this have to do with us? You know, what does a jar and an opening have to do with human beings? Well, let me just show you that by simply changing my drawing a little bit, you'll see what this has to do with us. Now, instead of having all the molecules inside the jar, I know that you know they're there. I can actually erase all this, and maybe I can change the shape of this a little bit to help you see what this could be. So let's say I make that like this and start drawing in like that. I'm going to keep all this kind of the same in terms of the way it looks. Maybe like that. And you can see now, instead of a jar, what I'm creating for you are a pair of lungs. So this is a pair of lungs, left and right. This will be right and this will be left. And it'll look something like this. And this one might go up like that, around that cardiac notch, and go like this. And then we have, of course, the opening, which if instead of calling it an opening, I call it a mouth. This would be my mouth. And I could erase the word opening completely, and I think you'll start seeing how this is basically what happens in our body. So our head represents the opening of this, and this could be the nose, and this could be the head, kind of a flat head I have drawn here, but you get the idea, I think. So there's your nose, and there's your ear, and basically air is coming in the mouth and going into the lungs and back out of the lungs. And what we call this process is inhalation. So when you increase the volume, we call this inhaling. So if you've ever wondered, it's exactly what happens when you inhale air. There it is. And when you close up the lungs and air molecules move out, we call that exhaling. Actually, I should probably try to make it look the same. They're both equally important, so I'll draw them the same way. Exhaling. And now you can see how inhaling and exhaling happens. So with every breath, this is the process. You kind of subtly change the volume, and all of a sudden the pressure changes, air moves in and out.
Nice. All right. I'm just curious how long.
So we talked about inhaling and exhaling.
Yeah, like 8 minutes, 4 minutes, and it's like 20 minutes.
I've done a bunch of videos already.
Oh crap! Wait, what? Wait, what was that? Was that last one 20 minutes?
And exhaling. And I mentioned that the key first step for both of them is kind of this change in volume, right? Going up in volume or going down in volume. But I didn't really talk about how that happens exactly, so I thought I would kind of jump into that now. And let me begin by telling you that in the middle of your chest, you have this enormous kind of bone that goes down. And I'm drawing it out of proportion just to make it very clear where this bone is. But you can go ahead and feel on your own body this bone, which we call either the breastbone, or the more technical name is the sternum. So I'll write that down here. The sternum is this middle bone, and all of the ribs on both sides attach there. So you've got a total of 12 ribs and 7 pairs of them. Actually, I should say 12 pairs of ribs. I don't want you to think there are 12 total. We actually have 24 total and 7 pairs of the ribs. So 14 ribs actually attach directly to this bone, this sternum bone. So in white, these are the ribs. And between the ribs, you actually have muscles. So I'm going to draw in some of these muscles between the ribs. And these muscles are all going to have their own nerve that allows them to contract. So these muscles are controlled by your body or your brain, and their name, let me just jot down here on the side, is intercostal muscle. And inter just means between. This is the name of the muscle. And costal refers to the ribs. So when you see that word costal, you'll know we're talking about the ribs. So what's between the ribs is these muscles, intercostal muscles, and they're going to start moving outwards when your brain says, hey, I want to take a deep breath. So these muscles are going to contract, and the ribs, I should say, are going to move outwards. So these go out, and you also have, let me just make a little bit of space on this canvas, you also have another muscle that kind of rides down here and has kind of an upside down U shape to it. So I'm drawing it kind of like a dome. You can think of it as a dome. And this dome is the floor. If you remember, we talked about the floor of the thorax. So this is, of course, our diaphragm muscle. So we've got our diaphragm muscle, and this one, when it contracts, it's going to go, instead of going out, it's going to go down. So it's going to kind of flatten out. And I can actually draw this. If you can now just stick with me for a moment, I'm going to erase this dome-like shape, and I'm going to draw it, what it looks like as it contracts. So when it contracts, it's actually going to be more flat. And this flat diaphragm, as you can see, is now further down than it used to be. And as it goes down, all of the structures that are inside this space, so the 2 lungs, and of course I didn't draw the heart here, but the heart would be kind of in this cardiac notch. If you want, maybe I could even draw that heart here. This is our heart here. They're all going to kind of physically move down. So this is our heart and our lungs. They're physically going to be kind of drawn downwards and out. They're going to also move out as the intercostal muscle move out. So you have expansion of these lungs. That's basically the idea. And if you were to kind of zoom in on this to kind of see exactly what this expansion looks like, when I say, you have more volume in the lungs, really what I should be saying, if I wanted to be more exact, is that all of the alveoli, if these are the alveoli, let's say this is another branch and this is another alveoli right here, all these alveoli, they are actually expanding. And you have about 500 million alveoli, if you can just kind of fathom how big a number that is, it's an enormous number of alveoli. And if I was actually drawing them, I would be here drawing forever, right? It would take forever to kind of write out this many different alveoli. But basically what happens is that when the ribs go out and the diaphragm moves down, these alveoli are actually being pulled out. They're actually being pulled outwards. So they are actually going to be getting larger in size. They literally look like they've grown in size. And this is what they look like. And actually, if you were to take an even closer look, you'd see that these alveoli have around them a bunch of protein. The cells around them have a bunch of protein. And this protein is called elastin. And you can guess what elastin might do. It has kind of a similar sound to the word elastic. And elastin is basically kind of like a rubber band. So you can kind of think of elastin as a rubber band. And when the muscles move down and out and the alveoli are pulled open, let me actually now kind of scroll up because you can kind of go back to the idea of inhaling. What is happening then? Well, you have a couple things happening. One, you have muscles, I'll just write muscles contracting. Muscles contract. And when I say muscles, you know I'm talking about all those intercostal muscles in your diaphragm. And as a result of the muscles contracting, you have now the alveoli. Alveoli are stretched open. So those rubber bands, those elastin proteins, are literally physically being stretched open. So the alveoli are stretched open. And keep that in mind, because what's going to happen then is when the muscles relax, which is what happens when you exhale, when the muscles relax, what do you think is going to happen to that elastin? Well, if it's like a rubber band, if that's what I'm saying it's going to be like, then the alveoli are going to recoil. They're going to recoil. And that's actually the driving force for why the volume goes back down. So if you have a bunch of rubber bands that you're stretching out, let me actually bring up the picture, you'll see it really clearly. If you're physically kind of using your muscles to help pull this stuff open, then the moment that you stop pulling open, the moment that you stop contracting those muscles, now that you have a nice big volume, what's going to happen? Well, all these elastin molecules are going to snap back. Let me do it with a different color. Let's do this color. They're going to snap back like this. All that protein is going to want to snap back into kind of the original size. And when they do, this thing gets smaller. So my alveoli kind of goes back to its original size, which was much smaller than this. Let me actually just quickly show that and show you that even though contraction is what opened up things, it's the recoil that kind of brings things back down to their normal size. And let me erase this to make it kind of a neater drawing. So you can see it now. Inhaling, the way that we actually increase the volume is by pulling things open through contraction. And this actually requires energy, right? Remember, you can't contract a muscle without spending chemical energy. So this takes chemical energy. And we usually think of this molecule ATP as the specific type of chemical energy we're going to use. And to exhale, when you reduce the volume, it's going to be driven by this elastic recoil. So that's a type of elastic potential energy. So this process of kind of inhaling and exhaling is really a little different from each other. On the one hand, you're using ATP, you're actually burning through these molecules. And then when you exhale, you're actually not using chemical energy anymore. You're just using that elastic potential energy. Kind of the same sort of energy that you can imagine you would have if you snap a rubber band. So let's stop there and we'll pick up in the next video.
Great. So wait, this one is 4 minutes, and then the next one is 20 minutes?
If you have a dog...
Or 5 minutes. The next one is 20 minutes.
Already on respiration, I think.
What? 20 minutes on lungs and pulmonary system? Okay.
If you've ever played fetch with a dog, you've probably noticed that after you've really abused that poor animal and run it into the ground, you've probably noticed that it started to do something interesting. It started panting. Did you ever stop to ask yourself why dogs pant? Well, here's your chance to answer that question. See if you can come up with a reason. Well, it turns out that the main reason that dogs pant is so they don't overheat. So let's take a look at how that works. Let's say here we've got our favorite little puppy, and it's just been running around for an hour. And it's panting, and it's got its tongue lolling out like they do.
Oh, dog.
Well, what's going to happen when that dog breathes is it's going to breathe in cool outside air. Let's say on that day it happened to be 70 degrees Fahrenheit. And it's going to breathe out hot air. Because the air that it breathed in is going to equilibrate with its body. And if you don't believe me, put up a hand to your mouth as you breathe out and feel how hot the air is that you're breathing out. What this means is that the dog is expelling heat every time it breathes because it's taking in something cool and putting out something hot, and that heat has to come from somewhere. Now for dogs, this is really important because they can't sweat. They have fur coats, and they couldn't very well soak those fur coats in sweat every time they want to lose some heat. So this is really their best way of getting rid of heat. Now we humans, and I'm going to try to draw one of we humans over here. We humans can sweat. This is a human with an afro, apparently. We humans can sweat, and so this method of losing heat by breathing heavily is definitely less important for us, but it actually still happens. So just like the dog, when we breathe in, with the air that we breathe in, which technically comes from both the nose and the mouth, that air goes into our lungs, and in our lungs it divides into all those little alveoli that you heard about that have a huge amount of surface area. Let me just draw a couple of them here. All these tiny alveoli have a huge amount of surface area, and that allows all this cool air that you breathe in, which I'm drawing here, to equilibrate with the temperature of the blood that's passing by these capillaries. And so just like the dog, when we breathe in air that's, let's say, 70 degrees Celsius, we're going to breathe out air that's pretty much body temperature. Whoops, that should not be Celsius, that should be Fahrenheit. When we breathe in air that's 70 or maybe cooler, we are going to breathe out air that's body temperature. And if this guy is not having a fever, that would be about 98.6 degrees Fahrenheit. So therefore, we can see that getting rid of extra heat is another thing that the lungs can do. And we have a fancy word for this. We call it thermo meaning heat, just like a thermometer measures temperature, thermoregulation. So you could say it's regulation of the temperature of our bodies. So that's another thing that the lungs can do. Lungs can thermoregulate. And you'll note that this is kind of convenient because times when you might be overheating, just like this dog, times when you might be overheating are when you've done a lot of exercise. And when you've done all that exercise, you need a lot of oxygen to feed your muscles. And at the same time, you want to get rid of heat. So these two functions of providing oxygen and getting rid of excess heat kind of coincide nicely in the case of exercise. Because what happens when you exercise is that you start breathing really heavily. So at rest, you might be breathing about 5 liters of air per minute, meaning that a total of 5 liters of air is coming in and out of your lungs every minute. But while you're doing exercise, let's say heavy exercise, let's say you're running a mile and trying to get a really good time, you can easily go up to 50 liters per minute. And clearly that is a lot more, 10 times more. So what that means is you're going to be putting out 10 times more heat through your lungs than when you're resting. So it's convenient that when you exercise, you get more oxygen by breathing heavily, and you also get rid of more heat by breathing heavily.
Okay. Here, what if you just take a break before this 20-minute video while I do something real quick, because I feel like I have to. And
Saf said, I kinda need to get this done ASAP
Oh,
cause
really?
it's late.
Oh, then shoot. Let me just do this real quick. Oh, Discord. Here. Here. There. Here. There. And we'll do both of them. Here we go. Okay, there you go. That's all I wanted to do.
Datsy Boy sent multiple files.
There you go.
Saf said, "Lol, nice."
Yeah, we can look. We can look at them in a minute. Maybe I shouldn't have sent them. Just go ahead.
Even before those videos, you had a sense that we need oxygen. And that we release CO2. And if you watched the videos on respiration, you know that we need the oxygen in order to metabolize our food, in order to turn our food into ATPs that can then drive other types of cellular functions, or anything that we have to do, move or breathe or think, or everything that we have to do. And then through the process of respiration, we break down those sugars and we release carbon dioxide. So in this video, what I want to do is kind of take a big step back and think about how we actually get our oxygen into our body and how we release it back out into the atmosphere. Another way to think about it is how we ventilate ourselves. Ventilation. How do we get the oxygen in, and how do we get the carbon dioxide out? And I think any of us could at least start off this video. It starts off in either our nose or our mouth. I always have a clogged sinus, so I often have to deal with my mouth. I sleep with my mouth open often. But it always starts in our nose or our mouth. So let me draw someone with a nose and a mouth. So let's say that this is my person. Maybe his mouth will be open so that he can breathe. So this is, his eyes aren't important, but just so that you know it's a person. So this is my test subject, or the person I'm going to use to diagram. That's his ear. Maybe he has a bit of a, let's give him some hair. Oh, maybe some sideburn. Anyway, a mustache. All of that is irrelevant, but this is our guy. This is the guy that's going to show us how we take air in and how we take air out of the body. So let's go inside of this guy. Maybe I can draw his outside first. Let me just see how well I can do this. So this is outside the guy. Oh, that doesn't look right. So let's say the guy looks something like this, and then, this is his shoulders. Just like that. That's our guy. All right. So in our mouth, we have our oral cavity right there, which is just the space that our mouth creates. We have our oral cavity. I could draw our tongue and all of that, and maybe I will. Maybe I'll draw the tongue. Maybe the tongue looks something like that. But you have this space inside of the mouth. I'll call it the oral cavity. So this space inside of our mouth, just like that. This is the oral cavity. Oral cavity. Oral for mouth, cavity for space or hole or opening. And then also you have your nostrils, and they open up into a nasal cavity. So they open up into a nasal cavity. So that's another big space just like this. And we know that they connect at the back of our nose or at the back of our mouth. And this passage right here where they connect is called the pharynx. This is the pharynx. And that's, when your air goes through your nose, they say breathing through your nose is better, probably because it gets filtered by your nose hairs and it gets warmed up and whatnot. You can breathe through the side. The air goes in through either your nasal cavity or your oral cavity and then comes back through your pharynx. And then the pharynx splits into two pipes. One air can go down either one, but the other one is for food. So your pharynx gets split. In the back, you have your esophagus. In the back, and we'll talk more about the esophagus in a future video. In the back, you have your esophagus, and in the front, let me draw a little dividing line there. In the front, let me make it connect like that. Actually, I was using yellow. I'm going to use yellow to continue, and I'm going to use green for the air. So it divides just like that. So this is the dividing line. So in the back, or the back of your, behind your air pipe, you have your esophagus. Let me make that another color. So this right here is your esophagus. And then right here is your larynx. This is your larynx. And I'm going to concern ourselves with the larynx. Esophagus is where your food goes down. We know that we eat food with our mouth as well. So this is where we want our food to go, down the esophagus. That's for food. But the focus of this video is our ventilation. What do we do with our air? So I'm going to focus as the air goes through our larynx. And the larynx is also our voice box. So as you hear me talking right now, there are these little things right about here that are vibrating at just the right frequencies, and I'm able to shape the sound with my mouth to make this video. So that's also your voice box, but I won't focus on that right now. It's called a voice box because it's this whole anatomical structure that looks something like that. But then after the air passes through the larynx, this is on the way in, it goes to the trachea. So then the air goes into the trachea just like that, which is essentially just the pipe for air. The esophagus is the pipe for food. Let me write this down right here. So this right here is our trachea. And then from the trachea is actually a reasonably rigid structure. It has cartilage around it. And it makes sense that it has cartilage. You don't want, you can imagine like a hose, if it bent a lot, you wouldn't be able to get a lot of water through it or a lot of air through it. So you don't want this thing to bend a lot. So that's why it needs to have some rigidity. So that's why it has cartilage around it. And then it splits into two tubes. And I think you know where these two tubes are going to. And I'm not drawing this in super detail. I just want you to get the idea of them. But these two tubes are the bronchi. Each one is a bronchus. These are the bronchi. These are the bronchi. And they also have cartilage, so they're fairly rigid. But the bronchi keep splitting. They keep splitting into smaller and smaller tubes. Just like that. At some point, they stop having cartilage, so they stop being reasonably rigid, but they keep splitting off. So I'll just draw them as these little lines. At some point, they become such thin things. They just keep splitting off, so the air just keeps splitting off and spread and goes down to different pats. And when the bronchi no longer have cartilage around them, they're no longer rigid. The first of those are called, or actually all the tubes after that point are called bronchioles. These are bronchioles. So for example, that you can call a bronchiole. And there's nothing fancy here. It's just a pipe that just gets thinner and thinner and thinner. We've labeled the different parts of the pipes different things, but the idea is let's take it through our mouth or our nose, and we just keep dividing and keep dividing. This main division into two different pats, that takes us into each of our lungs. So let me draw this guy's lungs here. So the lungs, so that's one of this guy's lungs, and that's the other of this guy's lungs. And these bronchi, or the bronchi split into the lungs, the bronchioles are in the lungs, and eventually the bronchioles terminate, and this is where it gets interesting, and they keep dividing smaller and smaller, thinner and thinner and thinner, into these little air sacs. These little air sacs, just like that. At the end of every super small bronchiole are these little air sacs. Super small air sacs. I'm going to talk about these air sacs in a second. And these are called alveoli. Alveoli. So I've used a lot of fancy words, but the general idea is simple. Air comes in through a pipe, the pipe gets thinner and thinner and thinner, and they end up at these little air sacs. And you say, well, you know, how does that get the oxygen into my system? Well, the key here is that these air sacs are super small and have very, very, very thin walls, or I guess thin membranes. So let me zoom in. So if I were to zoom in on these alveoli, just to give you an idea, these are super duper duper small. I've drawn them fairly large here, but each alveoli, let me draw a little bit bigger. So let me draw these air sacs. So you have these air sacs like this. You have these air sacs, and then you have a bronchiole that's terminating in that air sac. Maybe a bronchiole is terminating in another air sac, just like that. Another set of air sacs just like that. Each of these are only 200 to 300 microns in diameter. So that distance right there, let me switch colors. That distance right there is 200 to 300 microns. And if in case you don't know what a micron is a millionth of a meter, or you can do it as a thousandth of a millimeter. So this is 200 thousandths of a millimeter, or you can think of them as, and this is actually a very easy way to visualize it. This is about 1/5 of a millimeter. So if I actually try to draw on the screen, if you made this full screen, a millimeter is about that far, or maybe a little farther than that, maybe about that far. So imagine a fifth of that, and that's how what we're talking about, the diameter of one of these things. And just to put in the whole scheme relative to cells, the average cell in the human body is about 10 microns. So this is only about 20 or 30 cells in diameter, or relative to the average cell in the human body. So these have a super thin membrane. And these have a super thin membrane around. So this, you know, if you view them as balloons, the balloon is very thin, pretty much one cell thick, and they're connected to the blood cell. Or actually, the better way to think about it is that our circulatory system passes right next to each of these things. So you have blood vessels that come from the heart, and they want to be oxygenated. In general, we want things that the blood vessels that don't have oxygen, and I'm going to do this in a lot more detail when I make the videos about the heart and our circulation system. With the blood vessels that don't have oxygen, deoxygenated blood is a little bit darker, looks a little bit purplish, so I'll draw it as blue. So these are vessels that are coming from the heart. So this is blue. So this blood right here has no oxygen in it, or it's been deoxygenated, or has very little oxygen in it. And the word for the blood vessels that come from the heart are arteries. Let me write that down. I'll review that again when we cover it in the heart. So arteries are vessels, blood vessels from the heart. And you've probably heard of arteries. And the vessels that go to the heart are called veins. Veins go to the heart. This is really important to keep in mind, because later on you're going to see that arteries don't always carry oxygen, or they're always not deoxygenated, and veins always aren't one or the other. We're going to go into a lot more detail when we actually cover the heart and the circulatory system. But just remember, arteries go away, veins go to the heart. So here, these are arteries. These are arteries going away from the heart to the lungs, to the alveoli, because they want the blood that's traveling in them to get oxygen. So what's going to happen is that the oxygen, is flowing through the bronchioles. I need to get new colors. Is flowing through the bronchioles and circulating around the alveoli, filling the alveoli. And as they fill the alveoli, the little molecules of oxygen are allowed to cross the membrane of the alveoli and essentially be absorbed into the blood. And I'll do a lot more of that when we talk about hemoglobin and red blood cells. You just have to realize that there's just a lot of capillaries. Capillaries are just super small blood vessels that allow air to pass, essentially oxygen and carbon dioxide molecules to pass between them. These have a lot of capillaries on that allow the exchange of gases. So the oxygen can go into this blood, and so once the oxygen, so this is the vessel that's coming from the heart, and then it's just a tube. So then once it gets the oxygen, it's going to go back to the heart. So once it gets the oxygen, it'll go back to the heart. Once it gets the oxygen, it goes back to the heart. And so essentially, this is the point where this vessel, this pipe, part of our circulatory system, goes from being an artery, because it's coming from the heart, to a vein, because it's going back to the heart. And there's a special word for these arteries and veins. They're called pulmonary arteries and veins. So this is going away from the heart to the lungs, to the alveoli. These are the pulmonary arteries. And going back to the heart are the pulmonary veins. Pulmonary veins. Now you're saying, Sal, what does pulmonary mean? Well, pulmo comes from the Latin for of the lungs. It literally means the arteries that are of the lungs, or that go to the lungs, and the veins that come from the lungs. So anytime people talk about pulmonary anything, they're talking about our lungs. They're talking about, or maybe something related to how we breathe. So it's a good word to know. So anyway, you have your oxygen coming in through your let me go back to this guy I drew, through your mouth or your nose, through the pharynx. It could fill your stomach. We can blow up our stomach like a balloon, but that doesn't help us actually get oxygen into our bloodstream. But the oxygen will come through our larynx, into our trachea, through the bronchi, eventually in bronchioles, ending up in alveoli and being able to be absorbed into what were the arteries. But then we're going to go back and then essentially oxygenate the blood. The red blood cells become red once the hemoglobin has, or actually more specifically, the hemoglobin becomes very red or scarlet once it actually has the oxygen. And then we go back. But at the same time, this isn't just about getting oxygen into our arteries or onto the hemoglobin. It's also about releasing carbon dioxide. So these blue arteries coming from the lungs are also going to release carbon dioxide into the alveoli. And these will be exhaled. So we have oxygen coming in. So we have O2 coming in. When we inhale, other things will be coming in, but the O2 is what gets absorbed in the alveoli. And then when we breathe out, we're going to have carbon dioxide that was in our blood, then it gets absorbed into the alveoli, and they get squeezed out. I'm going to tell you in a second how it gets squeezed, and then it gets squeezed back out. CO, the carbon dioxide. It's actually that squeezing out that actually, when the air goes back out, it can vibrate my vocal cords, and it'll allow me to talk. I'm not going to go into too much detail of that. So the last thing to consider about this whole pulmonary system, or about our lungs, is well, how does it force the air in, and how does it force the air out? And the way it's done is really kind of like you can imagine it as kind of a pump or a balloon. Is that we have this huge layer of flat muscles. Let me pick a good color here. So if these are my lungs, I have a huge layer of flat muscles right here. Let me color it in. Right below the lungs, and this is called the thoracic diaphragm. Thoracic diaphragm. And so when it's relaxed, it kind of has this arch shape, and so the lungs are kind of squeezed in. They don't have a lot of volume. But when I essentially breathe in, what's happening is this thoracic diaphragm is contracted. And with contracted, it gets shorter, but more importantly, it opens up the space where my lungs are. And so my lungs can fill up that space. So what it does is, it essentially, you can imagine, it's like pulling a balloon larger, making the volume of my lungs larger. And when you make the volume of something larger, so the lungs will become larger as my thoracic diaphragm is contracted and it kind of arches down, creates more space. And as the volume of something becomes larger, the pressure inside of them goes down. If you remember from physics, the pressure times volume is a constant. So your volume, let me write this down. So when we breathe in, our brain is essentially telling our diaphragm to contract. So diaphragm contracts. We have more space around our lungs. Our lungs expand. lungs expand to fill the space, we have less pressure here than we have outside, where we can view it as negative pressure. So air always wants to go from high pressure to low pressure. So air is going to flow into our lungs, and hopefully there'll be some oxygen there that we can then essentially go to our alveoli and then end up in our arteries and go back in the veins as oxygen attached to hemoglobin. I'll talk more about it in detail. And then when we stop contracting the diaphragm, it goes back to this arched position. It contracts. It's kind of like a rubber band. It contracts back the lungs, and it essentially expels the air back. And now that air is going to have a lot more carbon dioxide. And just to give a sense of, our lungs, I can look at my lung. I can't look at them, but they don't seem too large. How do I get enough oxygen in them? And the key is that because of this branching process, the alveoli, the inside surface area of the lungs are actually much larger than you can imagine, or actually than I could have imagined had someone not told me. So it actually turned out I looked it up. The internal surface area of your alveoli, so the total surface area where the oxygen can be absorbed in or the carbon dioxide can be absorbed out from the blood, is actually 75 square meters. 75. That's meters, not feet. Square meters. If you think about it, that's like imagine some type of a tarp or a field. That's almost 9 by 9, 9 meters by 9 meters. That's almost 27, roughly 27 by 27 square feet. That's the size of some people's backyard. That's how much surface area you have inside of your lungs. It's all folded up. That's how it gets jammed into what look like relatively small lungs. But that's what gives us enough surface area for enough of the air, enough of the oxygen to cross the alveoli membrane into our blood system, and enough of the carbon dioxide to go back in. And just to have a sense of how many alveoli we had, I told you that they're very small. We actually have 300 million in each lung. In each lung, we have 300 million alveoli. So anyway, hopefully that gives you a decent sense of how we at least get air or oxygen into our blood system and carbon dioxide out of it. In the next video, I'll talk more about our actual circulatory system and how we get the blood, how we get the oxygen from the lungs to the rest of the body, and how do we get the carbon dioxide from the rest of the body into the lungs.
Gosh. What? Wait. How fast was that? What the heck? How fast?
Saf said,
That was 2 times
2x
speed. That didn't even seem like 10 minutes. No, I know why it was 20 minutes. My goodness, that was the... Oh, I can't. Okay.
This guy takes forever to get to his point.
I couldn't imagine listening to that any slower.
Lol.
That was just such a long... I don't know. Okay, shoot. I got a stock auction. Minecraft. It crashed.
Oh no.
It crashed right when I just tried to... Because I'm like, dang it. Frickin' Prism, what the heck? Alright, well, is that all you needed to do?
Yep.
Oh, nice. Okay. I don't know if I'm gonna get back in the game in time, because I should have left more time, because it's like 2 minutes to the end, so I'll miss it again. But,
Ema go
okay.
eat, I think.
Oh, wait, what do you mean no? Oh, wait, no! Oh, I didn't know you were how long? Like, how long have you been gone?
My stomach finally woke up, lol.
Because, like, here, I just wanna, unless you can, like, I guess I'm more or less curious than what each.
Maybe about 2-ish hours.
What? 2-ish hours? What? For what? For eating?
Ema watch a movie while I eat.
For 2? I thought we were gonna, like, do stuff. What kind of movie? I thought...
HTTYD2.
That's funnily enough, I think I know what you're talking about. Just by the acronym. And you know what?
How to Train Your Dragon 2.
It's funny, me and my brother and his friend, before he left, we got in a little conversation. We just talked about it, and it's like, it's funny that, I've really seen, like, only the first, and maybe, like barely remember the second one. It's like, my brother said, oh yeah, the second one is so much better than the first, and I'm like,
same.
Well, I mean, the first one is good. I guess I don't remember the second one, but, I mean, you can't really have... That's why I'd say the first one's better, just because it's the first one. And, you know, yeah. But also, um, um, well, uh,
It might not be 2 hours IDRK, I'll LYK though when I'm back.
well, I would just say unless you wanna, we could watch something else while you eat, like that video I wanted to show you last night. Just since I was like, since we're here, and since like I didn't know you were gonna eat, and then movie, and then 2 hours, and I'm like, if it doesn't really, make it, just since I thought I thought we were gonna be able to at least do something after you were done with your stuff. So like,
Saf said, I need some time to just be before I interact with people most of the time. W.
oh, really? Oh, I mean, I guess I think I see what you mean by that, but I'm like, well, I guess I guess it's okay.
It's kinda hard to just jump into masking right as you wake up. W.
Mask. Wait. Do I know what you mean? I don't know if I know what it's masking. I mean, I think I know what you're saying. That's why I was thinking, like, if you wanted to, wait a minute. Hold on, because I don't know about this really. Like, and that's why I'm like, well, if we just still want to, if
this and not acting as depressed as I get.
This and wait, jump, but wait, what do you mean? You're saying hard jump into masking? Wait, but in false. Size acceptance of autism behaviors pool. Facing the need. I mean, I guess I didn't realize. I don't think I really knew this about you, but at the same time, I'm like, oh, I guess I get it, but I just didn't.
Lol.
I didn't. I mean, if this is what you'd prefer to do in terms of just waking up and such, because otherwise I was like, well, we could just watch something here now. If it well, now it really does make a difference. Because
it's like a stage performance. Gotta practice before I can do it.
I mean, I still get what you mean. I'm just getting like, I think you saw the video I was gonna do before you left last night, right? Like,
IDR.
It was the weapon tier list for Terraria. I think Premium Lord.
Yeah.
I mean, is that Any sort of interesting that you'd want to, you know?
Not really, sorry.
Oh, really? Because, like, I mean, it's not even. No, the fact is that he makes it interesting, or at least the video. Because I did recently watch it. It's like it was kind of. It was like just. That's what I'd say. I wouldn't particularly watch an hour and a half long tier list video, but it surprisingly was just, man, he's the Hectic guy. I mean, otherwise we could just watch the randomizer, because we didn't watch the randomizer either. We didn't watch that all the way through. But no, I mean,
I want to go watch my movie, sorry.
Yeah, no, I was gonna say, if you just want to do Dragon, no, that's cool.
I'll LYK when I'm back.
Okay. Jesus, gone. Alright. It's getting strange. Sunflower and tokens.
Huh?
Okay. Okay. Four. Four. The heck? Yeah, no, for saying yeah. Um, What the heck? Oh, okay. For a second, I was like, what the heck just happened? It's not. It's see. This is 3, 2. Okay. Jeez. What the heck? Isn't crap? No, whatever. So, okay. Okay. Didn't realize how. Okay. Yeah. There's okay.
Dat Seaboy said. At Obishane.
Okay.